Hi. So I'm going to talk about the functional graph library. There are at least 3 graph libraries for Haskell. The functional one is strange in that there's no single representation of a given graph. I have an agenda, a tiny agenda, everything in here. So when I wrote up a description of what I'm going to do today, I said I'd talk about view patterns. I can still do that, but I don't really have a motivation for it. It's something that FGL can motivate that if you want to do certain things in FGL, but I end up never using it. So I don't know. I can talk about that if you want. What I thought I'd go do first is run through the types in FGL. I mean, this isn't a whole lot of code that I've written, but it's enough that I think it would be hard to get through it. And I don't know that it would be as useful as just talking about the type. The types are like the what's going on, right? So I'll talk about FGL's types, and then these things in particular are FGL. And then DWIT is the program that I'm writing. It stands for Digraphs With Text, or it stood for Digraphs With Text. Now it stands for Hypergraphs With Text. For some reason it's a little costly to change the name of a GitHub repository, so I'm just leaving it the way it was. Okay, so do we all know what a graph is? There's a common definition used in math education. That's not what I'm talking about. I'm not talking about you have axes and then some plots of points. A graph, another definition of graph is network. So it's a collection of things called nodes and edges, which are pairs of nodes. Or directed edges, which are pairs of nodes where the order matters. Or labeled edges, which are pairs of nodes with a label. Confusingly, you would think the node is the thing that you're representing, but in FGL, node is used to mean the number that the graph, how would I say this? I'm using, Tikhon Jelvis wrote this. Okay, so imagine this is a graph. Each of these circles is a node, and what a node means in FGL is the number on this thing. But these things really, they have 2 characteristics. Usually you're using labeled graphs. You can use a graph that's just numbers, but usually you want those things in the graph to actually be things, like it could be people or whatever, addresses, robots. So there's a label, which is actually the data. And then the number is just a way to refer to the thing that's there, which might sound a little imperative. And I don't really know how to debate whether this is imperative or not. It feels, I don't know, it feels to me like the numbers feel like addresses. But I mean, you can look at the code that we never use IO monads or state or anything. So it is, in that sense, it's functional.
How do you get the outputs then?
I can't answer that until I go through types. Yes?
Do you have to pre-allocate the
No.
addresses?
No.
Okay.
No, it can start out as one thing, and then it can be a million things. It's fine.
Well, I meant like, how do you maintain the ordering of the numbers? Is the ordering of the numbers important in your graph, or is that generated at output time?
So there isn't exactly a sense, or there isn't an order on those numbers, except for the fact that like 1 is a smaller number than 2, right? So I mean, those numbers are, so there's an ordering on numbers, but there isn't really an ordering on the nodes in the graph. I mean, if you look at this thing, right? If you wanted to order these things, you could pick any order. It seems like a convenient one would be to make this one first and this one second and this one, wait, where is that one? That one third. But you could do anything. I don't know, the numbers, I don't know how to answer that. There's no real sense of order on the graph. There's connection, but there's no order. Unless you can make an edge that's called, a type of edge that's called put this before that. Right? You can call it whatever you want, right? Where a relationship between 2 things says this thing comes before that. So you can represent that. But there's nothing inherent to that representation that prevents you from making contradictory statements, like this comes before that and that comes before this.
Okay.
Okay, so we've talked about what nodes are. They're just integers. An L node, that means labeled node. An L node is a node and then something, right? So an L node of A is what you use to represent A's in your graph. U node, we don't need U nodes. So an edge is a pair of nodes. Notice that these edges, they're always directed. I said before they could be undirected. And like graphs generally, they can have directed or undirected edges, but in FGL, they're always directed. And then you can have a labeled edge. Node. So a labeled edge says, this is where the edge starts, this is where the edge ends, and this is the label on it. The reason these letters are different, I don't know, maybe I should look at the source. I'm not sure I'm connected to the internet though. So, am I? Not quickly. I use something called, so I define a mind map. What I use FGL for is to make a mind map application. And I define a mind map is a graph on these two types. So the nodes are expressions, and then the edges are roles. So it's not showing up here. I don't know why that is. I thought it would be in the source. But anyway, a graph is it's not a concrete type. It has two type parameters. So you have graph AB is a graph where the edges, or sorry, the nodes are of type A, and the edges are of type B. Okay.
So nodes don't even have to be integers.
Well, they do. I mean, they didn't have to, but they are defined to be.
The parameter is the label of the node, I think, not the identity of the node, right?
Mm-hmm.
Right, yeah. Okay, so the label, like if you made a structure that was robot, right? You can have a graph of robots and fights that describes how your robots have interacted, because all they ever do is fight, right? So in that case, you'd have a bunch of numbers that are the nodes, and then you'd have these L nodes where every labeled node is a pair of an integer, the node, and then the A is the robot.
So it really is an identifier, it's just a unique identifier.
Yeah. I mean, I really think of it as an address, or I use it like an address.
Yep.
Okay, so then the type adj, I don't know, maybe this stands for adjacency?
It does.
Okay. These are the things, it's a list of, right, this says it's a list of pairs. So the first thing in each of these pairs is the label on the edge. And then the second thing is the node that this represents connection to. So the way this is used is you could have an adj representing all the connections into this node. Wait, was that to or from? Yeah, okay. So we could have one adj representing all the labels into, or all the edges into this node, and another adj would represent all the ones out of it. So that adj would have three pairs. It says 4 is connected to 1, 6 is connected to 1. So given that the adj is about 1, we don't actually represent 1 in the adj. So an adj is a way of saying something is connected to the something, we don't know what without exterior information, is connected to all these nodes. And it includes the label on the edge. That's different from the label on the L node. Okay, so that's how you represent a neighborhood of something. Then there's contexts. So remember, your graph has these two parameters, A and B, which are the label on the node, or the label kind on nodes, and the label kind on edges. A context is what's going on in the neighborhood of some node. Here we've got links into the node. Oh, it says it right here, right? Links into the node, the label on it, and the links out. So this thing, if we represented a context, so yeah, before I was saying the adj doesn't have information. If we were using an adj to represent the neighborhood of 1, that adj doesn't actually include 1 in it. But the context would, right? The context would say, okay, here are all the edges going in. That's one of the edges. And then here's these two things represent that node 1. And this thing represents all the links out of it. This is, I don't know how to say that any faster than the code already says it. A decomp. Okay, so this is where it gets weird. You can have a graph and ask for a decomposition. You frequently do, where you say, give me something in the graph and tell me what's going on in the neighborhood of that thing. So that'll be one of the two things in this decomposition. Where'd it go? Okay, so it's an M context, AB, and then a graph. So Jelvis drew a picture of this. If you wanted to represent this graph by splitting out 1 and what's going on around 1 from the rest of the graph, then what you would get is, well, I haven't actually looked. Well, but you're going to get one of these things, right? You get a context that says, so where is the context? The context around 1 includes 1 and includes the label on 1 and includes everything going in and out. And then you've got the rest of the graph. So when we've got a graph, so suppose we wanted to like map a function across all the nodes in the graph. We would ask, or one way you can do it is to ask, okay, give me that graph that you have, give me some node in it and the rest of the graph in this decomposition. And then you process that, right? You change whatever that thing is, and then you recurse on the rest of the graph. And that is the thing that they use ViewPatterns for, which, while I don't have a justification in my own code, I might be able to find Jelvis's. Okay, so, I should explain what a ViewPattern is. Wait, do we care? Do you want to know what a ViewPattern is? It's really short. Okay, so this says everything, or this defines it. So you've got, the idea is you don't want to write this. It's just a little slow to write that. So you've got some size. You want to say, if that, wait, size is a function from types to integer. So consider the type. If the type is unit, then do this. If the type is arrow, something, something, then do this other thing. So ViewPatterns just let you write that a little faster. What you do is you say, you're defining this function size for some argument, which when you apply the view function to that argument, you get unit. So if when you apply view to the thing, you get unit, then size of that is 1. The other case is when you apply view, you get an arrow. And if that's what happens, then do this.
Is that a Haskell extension?
Yeah.
Okay.
Yeah. Called ViewPatterns. So then he uses it. I don't know. I don't really have a motivation for this. Well, but you can see what he does, right? If he wanted to write this unsafe head function, I think it's unsafe. Actually, I'm not sure it's unsafe. Well, yeah, it is. So this takes a graph and it gives you the head of the graph. But the thing is, the head in FGL, the first element of the graph, like I was saying, you asked about order. There is no canonical order on these things. So it could give you anything. But you know that when you call ghead, you can, well, there's two, let's see. So here's where he's using the ViewPatterns extension. Right? He says, if when you call ghead, or when you call match any on the graph, you get a context and the graph. That's what we were calling a decomp. Right? This decomp.
Does this take a long time?
Does what take a long time? There aren't a whole lot of these. No, we're almost done with the types in
No,
FGL.
I mean, if you were trying.
Oh no, it's surprisingly fast. Yeah, I'll show you the data that I'm using, but it's like things happen instantaneously.
Well, the reason that it's fast is because it's unordered, right? So the first thing that's in the data structure gets returned, and you don't have to worry about the rest of the data structure because I would assume the rest of it's lazy.
Yes.
So the first thing that's available gets consumed, the rest of the graph is returned, and just ignore it if you don't need it.
That's right.
So
There are trade-offs. There is a speed argument well, I mean, really, I haven't, there's probably a list of arguments on either side for, there are some things that you can do faster with a this functional representation, and other things where you would want an array. But even for those things, like the difference is not, it does surprisingly well. Other people, like online, I've read those arguments, but I didn't really internalize them. But you can find them, arguments for why use this kind of thing. I'm using it not for speed reasons, but for just because it's really enjoyable language. I was, before FGL, I came to this from GraphDB, which is a currently unfinished thing by Nikita Volkov, which has all these crazy bells and whistles. It's I don't know the words for it, but there's all these tricks of type or data safety, where like when you write something, I don't know, somehow operations are verified, and it's like, I don't really know what he's doing. It seems good, but also really hard to use, and he didn't want to help me out. Whereas this stuff is so well documented, I didn't even need very much help. I needed some. I used the Haskell Cafe list a little bit. Why was I talking about that? Oh, you asked about speed. Yeah, I think that's all I can say about speed. It's, well, maybe not. So the thing about this functional representation is you can ask for a decomposition, and it'll give you this and the rest of the graph. You can have one operation that did that, and then some other operations that ask for different decompositions, and they end up recycling these different representations of the graph, so that it often doesn't have to construct a new decomposition. It'll just use something that it did before.
It tries to maximize sharing.
Yeah, which is an advantage that you get because there's all this equational reasoning you can do, right? If this was an imperative sort of thing where you do this to that thing and then you do this other thing, you wouldn't know how to use something that had been through a bunch of transformations aside from the result that you eventually got to. You know what that thing means, but you don't know what all the others are. Yeah. Okay, so we can decompose a graph. That's it. Okay, so then he defines the class. Here it is. So graph AB is a, wait, is that right? No, that's a method. Oh. Well, I don't know where GR is defined. But anyway, you see the way this is used. Oh, I showed you that already. Yeah, so if I wanted to find a kind of mind map, I say this is a graph where the nodes are expressions and the edges are roles. Okay, so let me go back to my list of, okay, I might have to talk about and match. No, I don't think I really do. I don't know. Maybe I'll come back to that. Okay, so now I will talk about the thing I made with it. So FGL represents the things where there's a clear distinction between nodes and edges. Right? Nodes are the things. Edges are the relationships between the things. I mind map a lot. I'll write a sentence, and then another sentence will be a child of that sentence, and I build trees of text. I really spend a lot of time doing it. I love it. I think I've mapped my mind like multiple times over. I wanted to be able to say, well, the relationship between two things, I want to be able to say something about that relationship. Right? So I would like that to be the child of some piece of text. So I wanted the distinction between nodes and edges to go away. That was one thing I wanted. Another thing I wanted is in FreePlane, and we've been looking at FreePlane. This is FreePlane. In FreePlane, the data is a tree. This thing is a child of that. These things are children of this. You can't give something more than one parent. But sometimes you would like a piece of data to be in more than one category. So what do you do? Well, FreePlane just won't let you do it. It'll let you draw these arrows, right? But those are totally different, right? The thing about the tree relationship is I can chase it down, right? I can say, okay, so here are my plans for the thing I'm writing. So this is a sort that I made on December 26th. So I can chase down things as far as I want, and and I can fold, right? I can say all that data, I don't want to look at it. Just show me its eldest ancestor. That's all I want to see of that data. the arrow relationship doesn't let you do that. You can click on it, right? If you, like, suppose this thing was very far away. Right, and I can see that there's something connected to it, and I can say, okay, show me what's on the other side of that. But that's annoying, right? I'd like to be able to use the mouse. I mean, I'd like to not have to use the mouse. Because it's fast, right? The keyboard is faster. And speed matters. If you've got a bunch of data theoretically representing all the stuff that you want to work with, but it takes too long to work with that stuff, then you're just not going to do it. Right? So, yeah. And by that argument, the speed argument, I have not, by any stretch, replaced freeplane yet, because the thing I've written is really slow to work with. But you'll see how I represent more than freeplane can represent today. Okay, so an arity, this is a term from math. It means the number of arguments to a function. So like the squared operator, if you have a thing called x, you can square it. That squared operator is unary, that is, it has arity 1. It takes one argument. So those, I wanted relationships to have arity, right? There could be the relationship, this needs that for that, or this contradicts that when in this context, right? You might have reason to use more than two things. So this will let you represent, my idea is to let you represent relationships between more than two things. So in that case, you need to be able to describe the relationship so you can say what the arity is. The relationship position of something is its place in such a relationship. So if you got this arity 3 relationship, blank needs blank for blank, then if something is in the third position, that's going to have rel pose 3, right? Relationship position 3. Okay, so once you've got those things, you can talk about, or maybe even before, you could talk about an expression. There's 3 kinds of expressions. An expression can be a string, right? Or it can be what I call a template. A template has an arity and a list of strings. So blank needs blank for blank. The 2 strings in that would be needs and for. Actually, there's 4 strings because there's the empty string. Maybe I should write this out. So in the relationship template, blank needs blank for blank, there are 4 strings. That's the first one. Needs is the second one. For is the third one. And that's the fourth one. Okay. Okay, so that template would have had arity 3, and then it would have had those 4 strings. There's a third kind of thing in this graph, which is the relationships themselves. And the relationship, if you look at the node, all the relationship knows is its arity. Now, in fact, the relationship is a connection between some things in the graph. But the node doesn't represent those connections. The graph will. So the relationship can only say, well, I represent a relationship between 3 things. And then you have to look at the graph to see what those things are.
So the expression is going to wind up being a label on a node?
The expression,
Is it
yes,
yeah.
yes. The expression is the label on the node. The node itself being an integer. Okay, so then there's a thing called a role. Things in this graph, every edge in the graph is a role. And a role is, nodes play roles in relationships. So like an expression, there's going to be, in that, I'll keep coming back to this, blank needs blank for blank. You consider the first blank. That is, occupying that blank is a role. And some node will have will take that role. Now in this if you want to talk about that relationship, there's really 4 parts of it, right? There's the 3 members, and then there's the template. So that's why I say this role can be either your role in the relationship is as the template, right? You are the template, or else you are in one of the positions. Maybe I should have called this in pose, but instead I called it as pose. Yeah. Is that clear? I don't feel like I'm explaining these things perfectly, but I'm not getting a lot of questions.
So where does it going to live, I think might help.
The edges are roles.
The labels on edges are roles.
Yes,
Okay.
yes.
So it's saying like, so you're connecting expressions with roles, and you can be one of 2 things. So you can say I fill position 2 of this template.
Yes.
You can say I am the template for this string?
Some rel, some relationship, right? So an expression is either a string or a template or a relationship.
So some rule, not every rule is valid for every combination of.
Correct. Yeah. Something should not be a template unless, or rather, it should not be used as template unless it is a template.
Yeah.
And I haven't really encoded, like I'd like to encode that in Haskell, right? That should be part of the type definitions. That appears in the functions, but yeah, I don't really know what to do about that.
That's tricky.
Do you have thought of using a fixed point?
No, I don't even know what you mean.
Well, there are certain functions that have fixed points, okay, and you can use that to anchor a computation.
It's a whole big thing. Describe what that is.
I know what a fixed, like I proved, I think I read someone's proof of the fixed point theorem, some fixed point theorem. I guess there's a lot of fixed point theorems, but no, in this context, I have no idea what you're talking about still.
No, but a factorial has a fixed point. Okay, greatest common divisor has a fixed point. So there's only a few kinds of functions like that.
Okay.
So you can use those kinds of relationships basically as templates themselves. Sorry.
I do not understand.
I'm just riffing.
Okay. Well, I'd be happy to, at any point when you become more confident of what you're saying, I'm happy to hear it. Yeah. I mean, I've heard sort of, it sounded mystical to me. I've heard other people talk about fixed points in Haskell. I've never understood why you would do it, or what they do even.
Do you have a question, actually?
Yes.
Do you have a like sample data or something that, like, can we look at a simple graph that has been written in this? I still haven't grasped
Simple graph.
what the relationship is between templates and things that aren't templates.
Sure.
I think it would be helpful to see.
That's a really good idea. Yeah. Excellent. Okay, so in this graph, this is one representation of a graph. If you ask FGL just to print the graph, it'll do this. And the ordering on the nodes in that case is kind of fixed, at least until you modify the graph, it'll appear in the same order. But anyway, in this representation of the graph, you've got a list of nodes and then a list of edges, and that's it. That's all the graph is. Okay, so the first item in this graph is the string dog. I'm going to say node 1 instead of the first item because that's confusing to get off by 1 errors. So node 1 is the template. It says blank wants blank. Node 2 is another template. Then we've got water and brandy. Node 5 is a relationship between 2 things. So is 6. Node 8 is a relationship between 3 things, which it uses this template. String to template is something which you give it a string and then it turns that into a template.
The only reason you know that it uses that template is because that template is the only one with 3 arity. Is that correct?
That's why I know it.
So
However, I can deduce it from this stuff. Yeah. Sure. Okay, so if we consider these 3 edges, right, the edges on this line, this says from node 5 that two-thing relationship. From node 5 to node 1, we have an edge with the relationship, or with the label as template. So that says the relationship represented at node 5 uses the template represented at node 1. And then this, it says the relationship represented at node 5 uses the string represented at node 0 in the first position of that relationship. And in the second position, we have node 4. So these three things, they represent the relationship dog wants brandy. These things represent the relationship. Let's see, this is, oh no. This says, I think, dog needs water. Yeah, the template is 2, so that's blank needs blank. And then we have 0 is the dog, and 3 is the water. Okay, so dog needs water. Then we have, well, this is just a three-thing relationship. So a relationship between three things is going to involve 4 edges, right? Because you have to say what the template is and then what the 3 members are. I don't use the word member in the code itself, but it's a useful word. So, okay, so this last one is interesting. Here's where I use a relationship to talk about another relationship. So at 11, we've got this 2-item relationship. And it uses the template at 9. 9 is the relationship statement blank is blank. So this says 5 is 10. That is, it says the relationship represented at 5 is dubious. The relationship represented at 5 was that the dog needs brandy. No, that the dog wants brandy. Okay, so this says that is dubious. Very good.
How? Because isn't the node at 5, I thought that was just, oh, rel isn't arity. Okay, I'm sorry. I was confused. So,
It's all good.
But so wait, rel does look like arity, because rel of 2 means 2 arguments, rel of 3 means 3 arguments. How does that thing that you just said, 5 is dog needs water is dubious? How is that represented? Sorry if the answer is like this.
So first we had so node 5 represents the dog needs, or the dog wants brandy, right? This is node 5, dog wants brandy. So this says, in short, it says node 5 is 10. Because the template is, okay, so the template 9, you know what I should do is I should load this into an interpreter and we can talk about, well, I don't know, maybe not.
I think I actually got it.
Okay.
Because we're not looking up, this is just the raw data to create the graph. This isn't the actual graph itself. So when we're talking about node 5 is node 10, we're actually talking about the template 9, where we're actually saying statement dog needs water is dubious.
Yes.
And that is a query on the graph itself, not the raw data to create the graph. So the combination, the thing that I was having a problem was looking up just in the first part of the thing, just in the nodes. That looks like you would just look up rel2, which isn't that interesting.
Right.
But what you're saying is that the query on this thing actually looks up the completed, created graph after all the substitutions have been made.
Yeah.
And that makes sense. Okay.
Yeah, I should have belabored, there's a distinction between like the underlying FGL graph, where edges are pairs, and then this graph that we're trying to represent, we are representing, where relationships are more than edges, right? An edge can only be two things, but a relationship can be any number of things with some kind of template that describes, you know, how those things are related.
Would a plain text node be a template of arity-0? Or just a string, rather? Because that would be, there's no need to have a template of arity-0 because you have plain string elements. So you can have, that's effectively the same thing, right?
Template equal, no, template arity-0 equals string. I like it.
No? All right.
Plan got. Thank you. Oh, there was something else I wanted to write about, or read about fixed points. Yes. Okay, so what are we doing? I guess we were working through types, but we might be done. Yeah. Yeah, okay, so now I can, well, I don't know what else to do. I didn't expect to finish so fast. I can show you, so what I did was I wrote, I haven't talked about the parser, which was, it's not as pretty as this code, but I don't know, maybe I should show you that. So this file lets me parse a free plane document. So these free plane documents, there's 4 things that I capture about this data. I don't capture everything about this data. First, some of this data can have HTML in it, or it can even have a picture. I'm just sort of throwing away that information. But in this data, you have the tree relationship, and you have an ordering on siblings, which is different, right? These things are all children of this parent, but that doesn't say what order they're in. So really, this information that you see right here, just in this generation and that generation, consists of 2 separate relationships. Every one of these things has a parent and a next sibling. So that's 2 kinds of edges. And then there's a third kind of edge, which I was showing you over here, right? The arrows, right? That's a different kind of way to connect 2 things. So this parser then, let's see. I mean, it takes a long time to define a parser. You have to say, okay, these say just how to parse a string given some parser, right? So how to apply a parser to a string. These say, like this says a lexeme, if you want to make a lexeme out of P, first parse P and then parse some space and return what you got from P and ignore the space. So you have to define a whole lot of parsers basically, and then you can finally, well, okay, so I should show you what free plane data looks like. Where am I? See, data. Okay, so here's some free plane data. First, you got a comment. I can't see my cursor. Okay, so this comment is something that I wrote a parser that recognizes comments and throws them away. And then you define some nodes. Okay, so first it defines the root of the graph. And then it does all this stuff that I don't know what it is, and I don't think I need to. So if it starts with a hook, I throw away that data. Then there's map styles. I kept the map styles. Oh, so that was the other thing. There's 4 relationships that I end up parsing, the 4th being font data. So these styles, they describe fonts. Okay, and then finally you've got, what is this? This is a node, and this says, I think I throw that away. Okay, and then this arrow length, this says that that node is connected to some other node. So it doesn't have an origin ID because the origin ID is implicit from the node, or from the previous node, right? You'll notice that there isn't a trailing slash on this caret here. So that means that information about this node continues into these next, what would you call them, lines of the file. So there's 2 arrows from that thing, one to the node with this destination ID, or what, rather the node with this ID, and another to a node with that ID. Okay, so that's the first node, and then here's the second node, each of these is simpler, right? So you see there's a trailing slash, so that says this is all the information you need about that node, aside from what's defined in its context. So the fact that this, man, where's my cursor? Okay, this first node, it's still open. We haven't seen a closing node for it yet. That means that these nodes are its children. And then you say, okay, we're done talking about that node, and we're done talking about whatever node came before that. So that's the kind of data that I had to parse. The way that looks, do you want to see the way that looks?
Sure.
Okay. So there's 2 arrows coming out of this guy. There are no other arrows in the graph. And then there's a bunch of these tree relationships. So this graph takes that much, in FreePlane, takes that much data to represent. Right, the styles take a long time. Oops. So, I don't know, I did that. I don't know. I'm excited about it, but I don't yet have anything to do with it that's particularly interesting to show you. I mean, well, I can show you what it's like to interact with this graph. Yeah, I should definitely, you deserve that. Okay, so let's see, have I loaded G? Nope. Oh shoot, I have to parse it again. Wait. Parse. Okay, so here's where I use all that parsing stuff. You can see I didn't do the greatest job of sort of working with, sometimes I work with the ethers, and sometimes I'm kind of fighting the ethers. Okay, so let's see if I have G now. Yes, okay. So that's what the graph looks like if you just ask for the graph. But now I can do things like this. I can say.
So you just parsed, did I just see, you parsed that file we were looking at into the graph, or is this is a different file it looks like?
Oh, this is agent.mm. This is, so, how can I introduce that? I haven't thought about that. Fresh? Yeah, that's where it is. Okay, so one of the things I have mind mapped a lot is what a person is, or what a thing that acts. That's an agent. So this is kind of about people, and it's kind of about machines, anything that makes choices. So like elements of an agent, they have things they can do. They have beliefs and models, preferences and goals. I shorten a lot of the words that I use because I use such a big font. I don't want to take a whole lot of screen real estate. But anyway, this is the sort of thing that I mind map. Everyone has lots of things that they think about, like what things in the universe are, and it's. I guess I should make the case for mind mapping. So why is mind mapping fun? If you spend a long time writing things that, like, suppose you're sitting and meditating, and every 3 minutes an idea occurs to you that seems worth writing down. So you write it down in something. Later on, when you're reading through that file, it's really intense because every one of those ideas individually was important enough to you that you thought it deserved being written down, but they were only coming every 3 minutes. And so it's like athletes do this with blood, right? They save up their red blood cells, then they absorb them in a concentrated, and they're like suddenly more athletic or whatever because they have more of the thing they do. They have it because of the concentrating power of a refrigerator and a centrifuge, I guess. So mind mapping is like that. Moreover, when you're going through things that you read, you can decide what parents they belong in. And it sounds strange, right? Because these ideas, well, particularly if you wrote down the initial idea, that is, if it came to you, you might think I've already processed that as much as I need to. But often that's not the case. And you come back to things. So for one thing, collecting a bunch of things that are about the same topic allows you to see insight into that topic that you wouldn't have otherwise. Like one of the things I've written a lot about is devnull. I call it the devnull because when I grep to search things, if I don't have if I just look for devnull, it shows up in a lot of places, but there's only one place that I've written the devnull, so that helps me find things. But anyway, so this is about how people throw away information, mostly. Maybe some of it's about computer science too, probably, but so what is it to want? Keep a collection anticipated less like, okay, so if you're collecting some things, if you make a collection and you think, I'm probably not going to review this as often as something else, should you keep that collection at all? That's anyway what I was writing about there. But my point is, you collect a bunch of ideas about some topic, and then when you look at them all at once, it helps you understand that topic. Either that, or it helps you understand your own understanding of that topic, right? Like if suppose when I read about devnull, I saw a bunch of depressing stuff, then I would see, I have a dark idea of what it is to forget something, right? And that would be interesting information that I wouldn't have about myself if I hadn't collected those things under one topic.
So when you put that information in then? So you're reviewing devnull, you realize that, okay, I had a dark idea about that. Would you just add that then, or would you like?
Yeah.
I'm leading to the question of like, so if I had a pen and paper, I would probably just like make a circle around it and like scribble like what's up or something, whatever. You know?
Yeah.
But you can't. You formalized it somewhat, so you can't really do that, right?
Yeah. So that's the problem with trees, right? What I would like to do is say like about those, right? I could say, okay, here are the original things that I wrote, and then on reviewing, I discovered dark. Okay, so that's one way you could represent that. But see, this is really unnatural. What you end up doing, and it's because we're trying to force this data into a tree, right? If you want to separate this stuff from judgments about it, then you have to push it down into a sub-branch, which sort of, like these two categories, they're getting in the way, right? What I would like is for this category to exist and yet not get in the way of these things. I would like these all to be that high. And often what I'll do to get around that is I'll color it green. To me, green just means it's about the others. Well, that's one meaning green has for me. But that's all internal, right? I want the computer to represent this data. I don't want to have to, I'm always ultimately it's English, right? So it's meaningless without a human interpreter. But still, you'd like the computer to have as much of that representation as possible. Okay, so that's my case. I didn't really think about how to make the case for mind mapping today. I probably could have done that better, but I find it very enjoyable, even sober. So
I'd be curious to learn a little bit more about FGL. Like we talked about the data structures a little bit, but what sort of functions do you use with it?
Sure. Okay, so what would you do? Let's see, is this the start of function? Yeah, okay, so here's types, and then empty is almost a type. It's a function that gives you an empty graph. Is empty, test whether there's something in there. Match, okay. So if you want to match a node and a graph, so what this function does is it takes a node and a graph, and it looks for that node in the graph. Decomp, so a decomp I guess is an M context. Decomp
with the rest of the graph.
Yeah. Okay, so if it finds the node, then you get that M context and the rest of the graph.
It is the rest of the graph. It does not include the thing that you searched for anymore. So if you search for it and then search for it again, you won't find it the second time.
If you search for it in the result of what you get, yes.
But you still get the context for things that refer to the first node, right? Otherwise, when you remove the node, you don't remove all things that point away from that node. well, otherwise you're losing part of the graph.
It gives you those two. Right, so the M context, let's
The
see.
M context gives it to you. The rest of the graph does not.
Right,
no longer have
right.
The context gives it to you though.
Yes,
It's not
exactly.
necessarily the M context. It's just the,
Oh, yeah.
because the M context is just maybe M context.
Right.
So yes.
Right.
Good.
So if the context can be found, then it gives you a context in the rest of the graph. Otherwise, it gives you nothing and the entire graph. Wait, where were we? Match. Okay, so that's an important thing. Make graph. That's you give it a list of nodes, list of edges. It gives you back a graph, and that's also one of the ways that it represents the graph for you. If you don't ask it to match anything, you just say, give me that graph. That's how it shows a graph. List of all the labeled nodes, match any. So this is like match, except you don't provide a node. You just say, give me some decomposition of the graph.
So I'm noticing here that the type of graph seems to be parameterized. What is GR? Is the
Yeah,
type of the graph?
GR is, well, where is it defined? Yeah, okay, so it's a class.
That's a class.
Um,
So there are multiple actual implementations, I suppose, with different performance characteristics.
Yeah, I guess you can roll your own. There's the easy way to do it. Maybe there's more than one easy way to do it. One easy way to do it that I've been doing is I just say, where is it? So I use capital GR to mean like the default graph. So this will give you a graph on these things and those things. But you can actually define your own if you define how to match. Let's see. So you need to define empty. You need to define these things, right? And the hard one is match.
So
Yeah.
Does FGL, FGL I'm sure provides at least one implementation of this type class. Does it provide multiples that have different performance characteristics or different benefits?
It provides at least two. There's one dynamic graph which has the operator and defined. It's a constructor. You take a context and the rest of the graph, and you use and between them, and then it gives you a new graph. And that's, for some reason, that's dynamic. And if you don't need a dynamic graph, then there must be some argument for both of them. I've only used dynamic graphs.
Okay.
And there might be other varieties of graph too. I haven't looked. I mean, I've only ever used these three libraries. I looked once in this and it scared me, and this, and I didn't even understand enough to be scared. Yeah.
It does look like there are several actual implementations of that type of class. It's like the Patricia tree and am I assuming correctly?
Yeah, I don't know.
Okay.
I can grep for class. Wait, what's instance? I can grep for instance. Where am I? Can I do that? Nope. Crap.
Instance graph GR tree.hs. Instance graph GR Patricia tree.
You know what I should do is go to CD.
It makes sense that you would basically just have different, ways of organizing these nodes, and some have different. Like maybe it's if you want to be able to insert, you have to do things differently.
Yeah, I believe
This
it.
one. Oh, so Digraphs is also a type class.
Yes.
It's not that concrete.
Yeah. Okay. Yeah.
That makes sense.
Yeah. They are alternatives.
Might be interesting to look into one of the simple ones. There was a basic one, right? I saw that in the list. I
On the
think.
fourth line?
Or maybe even tree.
Oh, you mean in the basic? So, Graph.hs I think is
That's probably
the most readable file.
There's the class.
Wait, so this is a class definition, but it's actually giving an implementation of match any?
Yeah, so you can give default implementations that refer to the other ones.
Oh,
It was just the minimum requirement where that was that list that you were showing us earlier.
where was that?
Minimum implementation.
Yeah, okay.
Yeah, minimal complete definition rather.
Okay, so match any is not. Yeah, you're right. Cool.
Because sometimes you can do more efficient than the default implementation, and you can override it.
Yeah, I wanted. So I feel like there's something inelegant about what I'm doing here. Right, I have this expression type, which it can be three different things,
Yeah.
and I would kind of like those to be their own types.
That's a very interesting question. So, I mean, maybe we can sort of write down what things can be what. So you can have a well, I guess if you say that you're going to use FGL, then you're sort of limited with what you can do. You can't have different classes of nodes. Like every node has to be the same kind of thing as every other node. Have the same kind of label.
Yeah.
So you can't, as soon as you say you're going to use FGL, you can't say like, well, there are two kinds of nodes and that have two different labels and two kinds of edges, and these edges can only point to these nodes. And you would have to modify FGL to get that.
That's another thing I've wanted actually is types in the graph.
Yeah.
Right? I mean, you can imagine if you could say these nodes are all dates, and then it's reasonable to do a query where like, well, suppose not dates, but dollar figures. Suppose there was a graph representing like stuff you'd bought, or yeah, and you wanted to say, okay, how much did I spend in September? I wrote down everything I did in September. So just find all the dollar figures anywhere, dollar figures that are descendants of some node, of the node September, and add all those up. Right? So if it could identify dollars, that would be helpful. And I mean, I can have the graph represent that. What I want though is for Haskell to understand that representation, right? So I can create a dollar, just a word. I guess I could create a relationship is of type blank, right? And then I just have the word dollar somewhere, and whenever I have a number, I could say number of type dollar, right? So the graph could encode that data. I don't know. I'm still working on it.
Here's a thought. What if you had multiple graphs where you had one graph and they could point at each other by having one pool of identities for the two graphs, so that you only have a node 5 in one of the graphs. And so if one of them is, if something in this graph is pointing at 5 and the node exists in this graph, like you try it in here, it's going to fail. You try it in here, it succeeds. You know? And then you could have multiple types for the labels. You have separate types for the labels of the different graphs.
Oh, I see. Yeah.
So that one of your graphs would have you would break up your expressions into maybe 3 graphs. Like you'd have a graph of strings, a graph of, I forget the other two, graph of,
Templates and rows.
yeah. And then you could probably wrap that to act like one graph. Again, you could make it probably a type class. You may not be able to implement the type class of graph, but maybe you could use a different interface.
What?
So you might not be able to compose these three graphs back into one
Right.
capital G graph,
Right.
but you might have a different API for it, but still get all the power of the FGL
Yeah.
and make it look like one thing.
That would be neat. Yeah, I don't know. Like, I can imagine that being better.
I have a question that is unrelated to that. So what is the advantage? So we've already explored collapsing a string into a template of arity-0, but what's the advantage of breaking out? What was your motivation behind breaking out the arity of a template out of the template itself? Because now you've got two things. One describes the other thing, but the other thing is that thing. So you can just ask it, hey, what's your arity?
What?
If you have a template, you can say, hey, you should be able to say to the template, what is your arity? Right? If you have a template, you
Yeah.
already know what the arity of the template is because it's defined in the template. Why do we need another arity? So if we can ignore a string, because that's a template of arity-0, and now we've just got template and rel, I've somehow along the line I've lost the plot of why rel exists. What is that? Because it seems to only contain an arity.
It's like it's an edge lifted up as a node, I think.
Yeah.
Like in his graph, not the capital G graph, but in what do we want to call it? In your mind map.
Mindmap.
In your mind graph, mind map, sure.
That term predates me.
Sure. So in the mind map, edges are nodes.
Yeah.
Are encoded as nodes in FGL. And so that's why there are two things in AXPR. There are edges and nodes, basically. And you can, because edges are nodes, you can actually then point at them.
What's the?
Right.
I thought that. Oh, sorry. Is that correct? First of all, is what he just said correct?
Every sentence was correct.
Okay.
Maybe there's a contradiction in the whole, but each sentence.
I'm on board. Then what? Because I thought that FGL already did that. Because now you've got nodes, and then edges represented as nodes, and then also edges in FGL. So now you've got two edges.
So the reason that you have to do this extra layer is because if you were just following the FGL model, you couldn't refer to an edge. You couldn't have a node with an edge to an edge. And you must be able to do that.
Understood.
Additionally, to have like an edge that connects more than two nodes.
Oh, so the rel arity is sort of a misnomer. It should be like rel pause, or not even rel pause, because you already have a rel pause, and that's where it is in the template, right?
Right.
But rel arity doesn't. Rel arity, maybe it says something to you. Rel arity doesn't say anything to me. If I'm looking at it, rel arity is just, well, yeah, there's loads of rel arities, but the node itself has a number at the end. Like the node has an address in your terminology.
Yeah.
And then the arity looks like extra data that is not necessary. So if you drop the arity off of rel, you should already be able to ask the template, hey, what's your arity?
Well, so certainly I can infer the arity from the strings, right? If I have this template is a list of strings, then I can figure out what the arity was.
In fact, it's stored in the template arity strings.
Yeah. Yeah, so, whoa, I just learned a new keyboard shortcut.
Control U and D? Or U and
Alt
F?
R.
Oh.
It's like Control L, but the reverse. Okay, so the template, I wouldn't have to encode the arity in the template, right? I could work out the arity every time by just counting strings. I just didn't want to have to do that. But there's, I think your question is why is there
an empty string equivalent to a, like you would, how would you count the strings? An empty string means a placeholder? What do you want to call it?
count the strings?
How would you calculate the arity if you didn't store it? It's not actually clear to me. Because it's not the length of the strings, right? Because some of the strings are content and not.
Yeah, so if the relationship is some blank needs a blank to fly, there's 2 blanks in there. So that's going to be a relationship of arity-two. There's 3 strings separating those 2 blanks. So if I just count the strings and then subtract 1.
And a blank is stored in the array of strings as an empty string in the list.
The blank itself is not stored. It just knows that it knows what comes before and after each string, each blank.
Oh, so it knows that between each string is a blank.
Yes.
Got it. Okay,
Yes.
so it's actually the length of the string is -1.
Yes. Yeah, that's
So-
why Devin's suggestion would work.
Yeah, that makes sense. So you really don't need either of the arities then, right? In the data structure.
You can always generate the arity based on the length of the string -1. The reason that this is interesting
From a template, right? From a
Yeah,
relationship. From a relationship. So I think there's a stronger argument. So it's really just for convenience that I have this arity, right? But for this arity, there's a data integrity argument. Where if the relationship, suppose the relationship didn't, if the node representing that relationship didn't know what its arity was, then I might have too many edges and I wouldn't know it was a problem.
Well, but don't you know which? Can we pull up maybe in a vertical split or something, horizontal split the?
How did I split it vertically? I don't know.
I have no idea. I don't know what to do next.
How do you split a horizontal?
Actually, I meant to say horizontal split.
Of course.
Nice. Thanks.
Can we pull up the? Devin asked early on for a sample of one of these graphs, and you pulled.
Yeah,
next to this?
the test.
Yeah. So the first, in each of these groupings, the first one, and of course they're just line breaks, they're not actually groupings in the data structures, on the edges. The first one identifies a template, is that right?
Yeah.
And so 11, 9, so 11 is rel2, 9 is string template. So like it would be an error if you, and it's as template. So you could actually like look for the connection coming from the relationship with an as template tag, right? It's an error to have one as template connected thing, right?
Yeah.
To a rel. So you could look for the as template coming from a rel, count its arity.
So would that be good?
Well, you wouldn't need to have arity in the.
Yeah, no, I see it. Yeah, you're right. That like it's not. I could do without it.
Yeah.
But it seems easier to have it, no?
Well, so the concern is that that's another. Now you've got 2 things that have no intrinsic relationship to each other. Well, they have no explicit relationship to each other, and that's a potential out of sync thing. So
Yeah,
that's
good point.
That's what I look for in these types of things.
You just got to think of it as like a cache, that it's, you're sort of caching that value. It might be nice to take that out of the actual core data structure in a more cache-like situation.
It might be nice to have the core data structure, and then for fast lookups, flatten that down into something that has all of these
Which you may not
duplicated.
really need.
Sorry?
Which you may not really need.
Right, if it's fast enough.
Yeah.
Yeah, but just from if we're talking about having the graph in memory, if every time that you do anything with the graph, you are querying and matching on arity, matching on arity as known by the template. So do the full lookup to get the template at the time that you're trying to add a new node to the thing.
Yeah.
And if that's an error, I mean, you've got a single point of truth instead of 2.
Yeah. You're right. I'm not sure If it was free, I would totally act on that.
Free?
If it didn't cost labor.
Oh, yeah. Well, I could write a regex for you if you'd like.
That's very kind.
I was messing around.
This is cool. It's really interesting.
Does it
Yeah.
scale for like, I'm probably the biggest noob in the room, for like the use case for graph databases that I've seen, namely Neo4j is for product recommendations on web scale stuff. In their marketing stuff, they talk about how whatever Walmart uses Neo4j for the similar products, scroll line that they cop from Amazon. And I was wondering if the limits that got mentioned earlier by, I think you, for how you can't have different types of nodes and edges would ultimately be the downfall of that type of use case for this.
So I don't know how it scales for big data. I can say for a graph with like 4,000 nodes, it's instantaneous. Or at least the queries, the kinds of queries that I run, which are like, show me all the children of this thing. Right? Those happen instantaneously.
What's the largest graph you've made with it?
The largest graph, what?
You've made with it?
I haven't really made anything with it. I've imported data from FreePlane into it. The largest graph that I've made from these principles is probably this one.
The other thing about the FreePlane data is it's going to be very tree-like. I
Yeah.
wonder how that impacts the performance of the graph stuff.
Well, so I
don't know.
wonder if you can't hijack the arrows from FreePlane to make a multi-parented node. Because even if FreePlane can't represent the multi-parent thing, you've said that the arrows are not super useful, but you can use the arrows to represent multi-parent in your thing.
You also mentioned
Yeah.
some conventions I use in FreePlane, like the green color and stuff.
Yeah.
You may be able to pull some more structure out of.
So I can show you how what it looks like, that FreePlane data, when we get it into this, I can show you what that looks like. Should I do that?
I think it'd be interesting, maybe not to walk through every single node as we did
No,
with
we
this
wouldn't do
graph,
that.
because it would be impossible. But
Maybe you showed a simple FreePlane one that just had about half a dozen nodes or something.
Yeah.
That could be interesting.
yeah,
Do you-
the 7 plus, or the plus 7 and
Wait, so you want to see
what's
a,
that one actually? Yeah, the G.
This one.
Yeah.
okay, what was that? Root plus 7. Okay, what's here? Root plus 22-ish.
The MM is driving me nuts because it's Objective C++'s file extension too.
Oh, that's too bad.
So like I always see Objective C++ files when I look at this.
You try to compile that, it will not
Mindmap. No, I don't think so.
So you want to look at this kind of map or a giant map?
Start with a small one.
Okay.
What did you have loaded in GHCI already? Because you printed a map. And
Yeah,
then
that was agent.mm. That's a big, that's this.
It is. Can you show how to query that? Not to hijack your question.
Yeah.
But
Yeah. Yeah, that's like my favorite thing.
Cool.
Okay, so I can say match, is matchrel, is that something I wrote? I don't even know. Matt, I had it. Okay, that's mine. So I can say, oh, of course, yeah, because no, FGL is better than using this kind of notation. Anyway, what this says is, in G, show me every relationship that has the following form. The template is 32, is the one defined at node 32. And the first member is undefined, so it could be anything could be there. And then the second member is 400. So this said, so first I should show what 32 is. Show expert G32. Okay, so this is the relationship. Blank has the Mindmap tree relationship to blank. So here you'd have the parent, and here you'd have the child. And then when I do this, I say, okay, so that's what 32 is. So this whole query is saying, show me every relationship from anything to 400.
So that'll get the context to 400. Right?
What?
That might get the context
Yeah,
to
yeah,
400.
yeah. It is in some sense the context of 4. It is the context using this relationship. It is every node that leads into 400 in this relationship. So it's every relationship where 400 occupies the second spot in this template.
And that's why rels are important, because that would not be representable in FGL.
I'm a bit lost, but I'll take your word for it.
I think that I've got that. I think I understand that. Hit paste and hit enter and let's see what happens. Oh boy.
So then it says there's just one, right? So there's only this node 400. It is an only child of node 1751. So then I can say, what's at 1751? Oops, that's 1851. So this is the relationship. Wait, what? Okay, no, yeah, so that's this, right? So before when I was saying, show me everything that's the relationship from something to 400. Here's what it is. All life has blank. 400 is optimization. So this is a way of saying all life has optimization. There must have been more context to this. It's not hugely meaningful, but out of that context. But let's see. Okay, so we can find out what was the parent of that thing, of 990. And then what is that? Okay, so now I can say, what is it? View ng so pre is something from FGL. I didn't write pre. But what it does is it gives you every edge coming into something. So, well, okay, so first I'll do this without the view. So if I just say, show me the pre, it's the predecessors, that's what it stands for. Show me the predecessors in G of 990? Yeah, no, of 572. Okay, so that doesn't mean a lot until we ask to view it. View G. Okay, so these are all the children of biological development. One of them that says what font that node has. Most of them are the Mindmap relationship. So world trade. What? I haven't actually read this file in a long time. So yeah, I don't know what I'm writing about, but anyway, this says that these things on the right side are the children of this thing.
Is this saying that all life has world trade, all life has leisure, all life has knowing, all life has...
I think so. Let me find by all devel. Yeah.
Oh, I see. So yeah, so it's showing in reverse order, which is probably just a...
It's an artifact of the parser.
Yeah.
But there, it knows about the order. It knows the right order. It's just that I have yet to write the thing that it looks for those. There's a read this then that relationship.
There's a parent and then like a next sibling thing, right? You mentioned.
Yeah.
So this relationship is the parent relationship. We're
Yeah.
not reading the next sibling.
Yeah.
So it's in an arbitrary order depending on the order is read in the file, probably because it probably assigns sequential IDs.
Yeah. Well, it uses the IDs that were in there, but
okay.
The order that it gets is it reads through that file, and the order in that file matters, and then it loads into the new file, so they end up in reverse.
I see.
Yeah, and arguably that read this then that relationship should be ternary, because you would say in the context of some particular parent, read this then that.
Mm-hmm.
I haven't implemented that. I'm not sure if I will or not.
Yeah, that's interesting.
planning to build a replacement for FreePlane?
I want to.
GUI and everything?
Yeah.
Awesome. And how long have you been, when did you start on it?
I wrote a prototype in Python in the summer of 2014, and then I took like a year learning Haskell.
Nice. Well, it seems like a library that a lot of packages use. I was just looking, 76 pretty mature looking packages on iPage, and it must be pretty good.
Yeah, I'm excited.
Foundation, I think.
How would you do like a weight or a graph with weighted edges or weight graph? Is that similar to how you would do templates here and have extra nodes that represent the edges themselves? Or?
How would I represent weighted edges?
Yeah, or a graph. With
Okay, so I could, if there's an edge from A to B, right? Like suppose A stole the bacon from B, right? And there's a weight on that relationship. What I could do is I could take that relationship, treat it as a node, and say the weight of this node is, or the weight of this relationship is that.
Yeah, so similar to what you're doing.
Yeah.
Yeah. Okay.
Can the edges also be given labels?
Can the edges be given labels? In FGL, yes. In DWIT, there's not really a distinction, right? There's no nodes and edges and labels in DWIT. That language doesn't exactly apply, but there's expressions which are either statements or templates for relationships or relationships. There's expressions, and then there's roles in a relationship, and those are all the things that DWIT is made out of. So kind of yes, but not with that language.
This is a new word you're using, DWIT?
DWT, Digraphs With Text, the thing I'm writing.
Okay.
Where can we find it?
On GitHub, under Jeffrey Benjamin Brown.
You can put a link up on the meetup comments, perhaps.
Yes, we'll do that. Okay, so this is data, and then this is that thing. The data is all currently FreePlane.
Cool.
Jeff, I'm going to be talking about many of the same things that you touched on.
Awesome.
I have a different slice of it.
I'm excited.
It's completely different. Has a different flavor.
Well, thanks very much.
Cool.
Yeah, thank you.